For a very long time, the Big Bang theory has served as the foundation for our comprehension of the universe's beginning. It is believed that an unimaginably dense space served as the starting point for everything we see today, including stars, planets, and life itself. This little stone, more modest than the top of a pin, detonated in a monstrous occasion that made the universe extend and develop north of billions of years. Even though the Big Bang theory is widely accepted, new scientific discoveries continue to raise questions about its predictions. The send-off of NASA's James Webb Space Telescope, JWST, the biggest space observatory at any point constructed, was expected to reinforce the theory of the universe's origin by giving authentic experiences into the universe's beginnings. However, JWST's discoveries, made only a year into its mission, surprised scientists and revealed possibilities that may alter our understanding of how the universe began. Astronomer Rohan Natu made one of the most surprising discoveries when he found a galaxy that defied all expectations while looking at JWST images. This massive, ancient galaxy, also known as Glass Z13, was formed hundreds of millions of years after the Big Bang. Not only did this discovery go beyond what scientists thought was possible, but it also sparked excitement and enthusiasm. JWST was intended to investigate the universe's earliest stages, a period known as the enormous daybreak. By looking at galaxies from this era, scientists want to learn more about the universe, including how dark energy and dark matter affect it. JWST's modest initial expectations included the discovery of some distant galaxies. However, the actual results have outperformed these forecasts, revealing a significant number of galaxies that defy existing models. The results of JWST's data collection could have far-reaching effects and usher in a new era of understanding the universe. This extraordinary explorer's extraordinary finds fuel the human quest to unravel its mysteries and reveal fascinating information about the universe's history. JWST challenges our current planetary models and questions how these findings fit into our understanding of the development of the universe by revealing old and massive galaxies. These inquiries challenge our understanding of how the universe as we know it emerged from a chaotic past and go beyond scientific curiosity. The first chapters of the universe's history could be rewritten by JWST's observations, not just of distant galaxies but also of our own existence in the universe that is always changing. "You build these machines not to confirm the worldview but to break it," said senior science advisor Mark McCarran at the European Space Agency. Even though JWST's observations have been made for billions of years, their impact on our understanding of the universe is only beginning. In 1985, early discussions about what would come after the Hubble Space Telescope, which was still years away from launch, kicked off the process of building JWST. Even though Hubble would be revolutionary, the team behind JWST knew that its capabilities would be limited by its reliance on visible light. JWST, on the other hand, was designed to see in the infrared spectrum, which enables it to look further into the universe and discover secrets from its infancy. When astronomers carried out the Hubble Deep Field observation in December 1995, the purpose of JWST became more apparent. The image revealed thousands of galaxies spanning more than 12 billion years of the universe's history, highlighting the requirement for more powerful telescopes to investigate even further back in time. JWST was launched on Christmas Day 2021 after more than 2 decades of development and a cost of nearly $10 billion. The telescope completed its extensive testing 1 month after reaching its destination in space, and in July 2022, it began its first year of scientific observations. The powerful events that took place during this initial phase, which is referred to as the First Revolution, were intended to shed light on the mysteries of the early universe. When astronomers spent hours searching tiny swaths of the sky for ancient galaxies, they anticipated making a modest find, essentially an improved version of the Hubble Deep Field. In any case, they were astounded. One of the JWST projects is led by Stephen Finkelstein of the University of Texas at Austin. He explained that these distant galaxies didn't appear until there were significant differences in the data from several projects. However, these galaxies appeared almost immediately, surprising the astronomers. Prior to JWST, the most distant galaxy was GNZ11, which was discovered in 2015 at a redshift of 11. Redshift estimates the extending of light because of the extension of the universe, with higher qualities demonstrating more noteworthy distance. Two independent groups, one of which is led by Rohan Natu, have identified glass Z13 at a redshift of 13 since the initial observations of the object. Researchers estimated the redshift based on light measurements rather than direct measurements in their haste to obtain quick results. The excitement persisted despite the fact that these straightforward calculations reveal galaxies that are bright and massive, with stellar masses equivalent to billions of suns, just like our own Milky Way. A number of candidate galaxies with redshift values of up to 20 emerged from various JWST events over the following days, indicating hundreds of millions of years since the Big Bang. Disk-like structures that were not expected to exist in the early universe were observed in these galaxies. In addition, evidence of mature spiral galaxies at a redshift of 10 was discovered by a different team less than 500 million years after the Big Bang. The standard model of the universe, known as lambda cold dark matter, lambda CDM, cannot account for the rapid expansion of such massive galaxies. It is necessary to carefully examine the conditions of the early universe in the moments following the Big Bang in order to comprehend this phenomenon. In the beginning, the universe was a dense, hot soup of primordial particles. Over the long haul, as it extended and cooled, helium and other light components advanced until the main iotas were shaped around 400,000 years after the fact. The first stars, mostly made of hydrogen and helium, formed around 100 million years after the Big Bang. Dark matter influenced the transformation of these ancient stars, which were both larger and brighter than the stars we see today, into protogalaxies. Nonetheless, JWST perceptions have tested this model by showing universes that are more brilliant and surprisingly huge. According to Stacy Moe of Case Western Reserve University, the small protogalactic components are not unexpected, suggesting that some galaxies were earlier closer, dustier, darker, and further away. The disclosure of these early worlds brings up significant issues about the beginning of the universe and features the need to modify our models persistently. The Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile made a follow-up observation of glass Z13 in August 2022 with the intention of doubling the initial observation. ALMA did not detect as much dust as glass Z13 had predicted, even when using lightweight estimates. Tom Bay of Goya University, who led the observations, said that this suggests that redshift light detectors can be eliminated. However, the galaxy was missed by ALMA, posing a challenge and confirming JWST's observations. The lambda CDM model's need for revision may be the most problematic explanation. These results are amazing and difficult to fit into our model of the universe, astronomer Michael Boinxian said, highlighting the magnitude of this potential paradigm shift. Modified Newtonian dynamics, MOND, is a controversial alternative explanation. ALMA's difficulty in detecting glass Z13 could also be explained by the dustiness of early universe galaxies. Early Charlotte Bricker and her partners recommended that JWST could have noticed significantly more modest systems in the early universe, demonstrating that the circumstances for star arrangement are better at this point. This idea is supported by David Spergel, who suggests that higher mass stars are more likely to form because of higher atmospheric pressure and temperature, possibly influenced by magnetic fields that were already present. The fast distribution of logical papers since JWST's underlying perceptions mirrors the shift to continuous companion audit on stages like AR-14 and web-based entertainment. Even though it might be quicker to share findings, there are concerns about making decisions before a full peer review. It is unlikely that every high redshift galaxies observed by JWST will be invalidated, despite calibration issues and potential recalibrations affecting some results. These galaxies' sheer number suggests that the early universe may have been different from what was anticipated. The odds of astronomers being completely wrong, according to Stephen Finkelstein, are slim, and he expressed confidence in the discovery's veracity. Using ground-based telescopes like ALMA and even Hubble, astronomers are rushing to perform spectroscopic follow-ups to confirm these galaxies' distance. To confirm its findings, JWST is also getting new spectroscopy capabilities. The ultimate objective is to ascertain whether the initial data collected by JWST can withstand further examination or whether the universe's first stars formed unexpectedly quickly. JWST was built to look for the first galaxies in the universe. In just a few months, it has made incredible discoveries that have changed how we think about the beginning of the universe. One thing is certain: as the telescope moves through space, the discoveries it makes will alter our understanding of the universe for future generations.